Three, two, one, and away we go. Another 2070 online section here at Iowa State. And today we're going to be talking about some characterizations of invertible matrices. So, we have introduced the concept of an invertible matrix, and we actually have basically a whole bunch of stuff that gives me necessary and sufficient conditions for a matrix to be invertible. A lot of things we've talked about, solving systems of linear equations, general properties of matrices, properties of linear transforms. There's basically a whole bunch of disparate pieces out here, and we are going to put them all together into a big ol' list for conditions that guarantee that a matrix is invertible. And we saw last time invertible matrices are very powerful, very important. And in practice, most matrices you're going to run into will in fact be invertible. So let's talk about the ways that this happens. All right. So here's our first list. Suppose that we have an invertible matrix. That means that there is a matrix so that when I multiply on the left, I get the identity matrix. Now, remember, the definition for invertible required multiplication on both sides. We're about to see we only need one. Ooh. All right, so that's true. Now, what can we do with this? Well, suppose that I had a matrix C that when multiplied on the left of the matrix A gets me the identity. Well, if AX equals 0, so if I'm looking at the homogeneous system, I can multiply both sides by C. Here we note good old matrix multiplication is associative, so I'm allowed to make that maneuver, and we arrive at X is equal to 0. So in other words, the associated homogeneous system of linear equations for the matrix A only has the trivial solution. So we talked about that. We talked about systems, homogeneous systems, and we saw that, hey, this is kind of an important situation because if we know you only have exactly one solution here, then you have to be row equivalent to the identity matrix. Right? That's the only thing that can possibly happen. Right? So if this only has one answer, well, then when we ref it down, we have to arrive at the identity matrix. If there is a big fat row of zeros at the bottom, well, then you've got more than one answer. So, you have to be row equivalent to the identity, and as we've already discussed, being row equivalent to the identity means that you are invertible. And look, we have closed the loop. If you started with an invertible matrix, then I can find a matrix so that multiplying on the left gets me the identity. That tells me that AX equals 0 has exactly one solution, and as we've already discussed, that forces you to be row equivalent to the identity, which we noted is equivalent to being invertible. There we go. So now we find that being invertible only needs multiplication on the left to get me the identity. I don't need to know it multiplies on the right to work. That's quite nice. And also, let's note something else here along the line. AX equals 0 having precisely one solution only happens when the columns are linearly independent. So you can throw that one into the mix as well. All right, so this gives us our first run-through of properties of a matrix being invertible. We find that it's equivalent to the homogeneous system having a trivial solution, the columns being linearly independent, being able to multiply on the left and get the identity, and being row equivalent to the identity. Got all that? All right, let's do it again. Suppose you have an invertible matrix. That means I can multiply on the right and get the identity matrix. Okay, now what can we do with that? So suppose I can multiply on the right and get the identity matrix. Well, then for any vector b, I can multiply that on the left by d, but by good old associativity, I can move my parentheses over, get the identity, and get b. So in other words, ax equals b always has a solution, no matter what vector b you have on the right. And as we've discussed, if that happens, then you have to have n pivot positions. If one of the columns failed to be a pivot column, well, then there is going to be a b we can find so that ax equals b does not have a solution. But I just said we have to have the solution, so it's got to be that way we've got n pivot positions. And if you've got n pivot positions, then you got to be row equivalent to the identity. Each column is a pivot column, which means that we have to see the standard basis elements all lined up, meaning that we get the identity matrix. And as we already know, being row equivalent to the identity gives us an invertible matrix, so we have closed the loop again. So now we find that being invertible is equivalent to finding a matrix so that multiplying on the right gets me the identity. That's also equivalent to AX equals B always having a solution, and that's equivalent to N having pivot positions. And furthermore, AX equals B always having a solution, recall that that means that the columns of my matrix span. Whew. Man. Pretty amazing that an invertible matrix has all of these properties. Maybe that's why they're like super important. I don't know. Alright, well, as mentioned, we had 4 bite-sized bits here to get to the full big ol' list, so where do we go now? So far we have investigated, okay, the algebraic side of being invertible. I can multiply on the left or the right and get the identity. We saw the connection to that with systems. AX equals 0 only has the trivial solution, AX equals B always has a solution. We've seen it connected to row equivalents to the identity or having pivot positions. We've also seen a connection to the columns being linearly independent, or the column spanning. Let's loop this now around to the linear transform interpretation of matrices, and let's recall that a function is said to be invertible if I can compose it with something and get the identity mapping. Very similar to multiplying and getting an invertible matrix. Yeah. All right, so formally, a function is invertible if I can find another function so that when I compose the two in either order, I get the same output. I just get the input back out. And as is tradition, the inverse is denoted by t to the -1, and that can lead to some confusing notational things, such as sine to the -1, which we usually don't write. We write arcsine. All right. Well, that being said, now that we've got the definition of an invertible function back in our mind, let's see how it connects to invertible matrices. So suppose I had a invertible linear transform. Okay, and let's let t of x equal 0. Well, then I can apply t inverse to both sides, and a inverse of a linear transform is also linear, and so it's got to map 0 to 0. And this means that, hey, if t of x was equal to 0, then x had to equal 0. And if we let our... Oh, spoiled it. That's fine, I forgot both of these. And as, if we let our mind float back, a linear transformation only sending x... the only thing it's sending... oh my god. Tripping on my words here. Let's try a take 2. Not one take in this one, unfortunately. So take 2 here. Right, so recall that a linear transformation, if it has the property that it sends x, if the only thing it sends to 0 is 0 itself, it must be 1 to 1. All right, now recall, now suppose we got a 1 to 1 linear transform. Well, for linear, we know we have a standard matrix A, and if ax is equal to 0, that's the same thing as t of x equaling 0, and that forces x is equal to 0, which means that A is an invertible matrix. Now, suppose that the standard matrix for A, for the linear mapping, is invertible. Define S to be the linear transformation defined by A inverse times x. Well, then if I look at T of S of x, I'll get x, and if I look at S of T of x, I will also get x back. So in other words, T is an invertible linear transform. So let's connect the dots here. So a matrix being invertible means that the linear transformation must be invertible. Closing the loop here. And we also see that invertibility of the linear transform, the only thing you actually need for that is 1 to 1. Pretty nice. Okay, so let's follow the thread here further with our invertible linear transforms. So suppose we got an invertible linear transform. For any b that lives in Rn, then t of t inverse of b is equal to b. So in other words, our mapping t is onto. Every element in the codomain has an input that hits it. Suppose you have an onto linear transformation, and let A be the standard matrix. That means for any b, I can find an x so that t of x is equal to b. So ax equals b always has a solution, meaning that A is invertible. And as we've already seen, if your standard matrix is invertible, then your transformation is invertible, so once again we close the loop. Pretty exciting. So, with all of that said, now we can compile it all together into this big old beautiful list. The following statements are equivalent for an n-by-n matrix to be invertible. A is row equivalent to the n by n identity matrix. A is n pivot positions. Ax equals 0 only has the trivial solution x equals 0. Ax equals b has at least one solution for each b. The columns are linearly independent. The columns span. The linear transform is 1 to 1. The linear transform is onto. There is a matrix, so multiplying on the left gets me the identity. There is a matrix multiplying on the right that gets me the identity. All of this guarantees that our mapping is, in fact, our matrix is, in fact, invertible. Exciting. Alright, so there's the big old list. Look at it in all of its glory. Now, it is worth noting that we did prove a couple of extra bits along the way here that aren't quite explicitly stated in the list, but are sort of implicitly defined. Here, the matrix C has to be the inverse of the matrix A. Right, and that you can kind of piece that together from the fact that A has to be invertible. Here, the linear transform behaving nicely. So if your matrix is invertible, we actually have a formula for the inverse. We saw it right here. So note that's sort of implicitly guaranteed by everything and not explicitly stated. And maybe you need to know this for a problem list or something. Okay. And along the way here, there are some other implicit things you can dig out of this as well. So, all right. Now, while this list is not completely exhaustive of all of the possible things that make you invertible, this is sort of the compact, nice, clean, giving us all the different ways we can view all of this stuff. Right here we see sort of the algebraic definition of being invertible, the matrix multiplication behaving. Here we see the linear transform interpretation of matrices behaving nicely. Here we see the columns of our matrix, which is what matrix multiplication was built off of, behaving nicely. Here we see the connection between matrix multiplication and solving systems behaving nicely. And here we see the row operations, the row reduced echelon form, behaving nicely. So all of these different ways to sort of view the exact same thing, and all of them coalescing and working together into this very beautiful list here. So, all right. So that's the rundown of the characterizations of invertible matrices. Oh god. Let's stop the video.